Hey guys, my name is Julien Leroux, and I'm the lead tools programmer in the Unreal Engine procedural team. And this talk is new tools for building photoreal worlds in Unreal Engine 5.2. So, sorry, double click. Let's start with PCG framework because that's the thing I work on. So, what is PCG framework? It's a fast and iterative procedural content generation framework in Unreal for world creators. So basically, we're trying to provide you tools so you can build your own solution for whatever procedural thing you want to do in your game, your movie, or any kind of project. So why are we here? Well, as you might know, in UE5, we released World Partition, and that allows you to build bigger worlds. And with bigger worlds, you need more content. And procedural is a pretty good way to approach that problem. So that's exactly what we've done in the Matrix Awakens demo. We've built this incredible city, all procedurally done, and it was awesome, right? But we kind of noticed there were some, production challenges, workflow issues that we wanted to try to address. And as you might have heard just a couple of minutes ago, with UEFN, more and more people are going to have their hands on UE, and we wanted to make procedural content generation a lot more accessible. So all of this drives the vision of what we're trying to accomplish here. We want procedural content generation in Unreal Engine, so no reliance on external processes, even though, you can add them if you want to. Runtime and live editing focus, so you can use procedural content in your games at runtime, or at least have a very good iteration speed in the editor. Because it's procedural and deterministic, you're going to have non-destructive workflows, and you're going to be able to do manual interactions, as you've seen in the demo. And finally, it's a framework, right? So it needs to be easy to extend. And we'll dive a bit more into that later. So the overall concept is nothing very new. Looks a bit like materials. Like materials, you have materials, material instances, and material graphs. So we're starting from the bottom here. We're introducing a new thing called the PCG graph, which I'm going to talk to you about in a second. At the instance level, we have the PCG component, which holds basically the graph you want to run, and at some point in the future, some parameters so you can tweak. And somewhere in the future, we're expecting to have, what you see is what you get assets that you drag and drop. You have a couple of sliders, and it just behaves the way you would expect it to. So let's talk about the node graph. It's an editor like, maybe something standard like the material editor. You're able to drag new nodes, drag pins, or in your right click, add something. There's a node palette on the left side, which will actually show the nodes you've created yourself if you want to. You have the settings on the right-hand side in this case, where you can tweak whatever you want. And because it's procedural, you want to be able to see the results. So any node you can inspect, see the results, the properties, the points, the metadata. You can also turn on visual debugging, so you can show cubes or whatever mesh you want. But as you might have seen already, everything is interactive. You change a parameter, it shows up live. You add a new node, it shows up live. You remove something, it shows up live. You can also change the landscape, and it'll update. So it makes for a very interactive experience, and it's very useful, and hopefully you guys will like it. So let's dive in a bit more on the data side of things. So conceptually, in PCG, data is a probability density function. So that means that you're going to expect density values from between 0 and 1. So let's take one example, the landscape here, right? If you're on the landscape, density is 1. If you're outside of the landscape, density is 0. Take another surface example. Well, if it's a texture, well, density can be driven by the pixel color, for example. So you can have values in between 0 and 1. That mathematical approach enables you to do intersections, unions, differences, interpolation, and be able to be very precise on exactly what you want to do. Concretely, we've already mapped a couple of engine types to be able to use in PCG. So landscape, you can raycast against the physics or overlaps. You can use splines, landscape splines, any kind of volume, primitives, collision shapes. But most of these you'll end up sampling from, and then you end up with points. And points are the core data type in PCG. So basically, points are very simple things: transform, bounds, density, and then some metadata. And metadata is what you're going to use, well, attributes, to build logic in your graph and come up with something cool. On the node side of things, the nodes basically, they do one of either two things. They do transform data, or they spawn or create artifacts, so spawning meshes, spawning actors, or any kind of resource you want to track. And PCG is going to help you to track those and manage those transparently. Of course, on the nodes, you can set up whatever value you want. Like this is a transform node, so you can say, okay, I'm going to change the rotation from minus 45 degrees to plus 45 degrees or something. But maybe more importantly, in native nodes, if you tag your properties as overridable, you can easily have the pins. Well, it's automatic, actually. You're going to have the pins so you can dynamically drive those values in the graph. If you're using a node created from a blueprint, any instance editable variable also will create those pins. And those pins will allow you to create logic and, in between the different data types or data in your graph. So let's say you build some trees. Maybe you want to put the roots around them, right? So you want to keep them in a logic way in your graph. Right. We're already providing you a small library of a bit more than 40 native nodes. But maybe more importantly, we're still providing you with blueprints. And that kind of ties in the next slide, which is extensibility. At the moment, it's very easy for a technical artist, or even less technical artists, to build a blueprint node for PCG. You derive from the PCG blueprint element class. You implement the execute with context method, and then you can use one of the loops we provide you if you need to loop on some points. And this loop is going to be multi-threaded by default. You just need to implement the body. And that allows you also to not only be quite faster, but sidestep some of the blueprint limitations, like the number of iterations. But you're still in blueprint, so you have access to everything in the engine. All right. On the execution side of things, I've already told you the nodes can be multi-threaded, and that's true. The graph itself can run multi-threaded as well. If multiple nodes, their inputs are previously computed, well, we can run them in parallel. But maybe a bit more importantly, for runtime purposes and live editing, everything can be time sliced as well. It's pretty simple to do, and it's something we can expand on in the future as well. And that's very useful for games that want to do runtime generation. Finally, we have a cache to allow iterations very quickly in the editor. So if you change just a part of the graph, well, we don't need to recompute the rest. It's already computed once. We've cached those values before. All right, so all of this is exciting. Hopefully, you guys are excited as well. But this is experimental 5.2, right? So don't get too attached to the UI or the API. We're still working on these. But we want to try to make these as simple as possible. So we'll streamline the APIs. We'll extend more stuff. And there's a couple of big topics that we're going to work on in the next couple of months and the next couple of releases. The first being graph LEDs. And JS will give you a good example and a good justification of that a bit later. We'll look into GPU microscattering soon enough. And we need to address a couple of production things, like per platform settings or different workflows. Sometimes you'd want to bake everything to the final game or something. But that's it for me. Hopefully you're still excited. And I'm going to leave you in the hands of the very capable JS to talk to you a bit more about the path we've taken to get to the electric beams demo. Thanks a lot, guys.
Thank you, Julien. My name is Jean-Sébastien Gay, and I'm a technical art director working with the Unreal Engine development team on procedural and world building. We started working on the PCG framework just about over a year ago, and we were able to build the Electric Dreams demo that was presented earlier in the keynote by leveraging all of the groundwork and internal prototypes that we did throughout that development year. So let me start by showing you some of the most important ones. It was clear for us that the framework had to support runtime and live editing. We started by doing gameplay prototypes in the Lyra Simple project as we think that there's nothing else quite like games to prove the point. As you know, in-game means unpredictable player input. And that's cool, that's what we want, that's what we love about games. But our procedural framework needs to answer to that with predictable, deterministic, procedural outputs. And that's extremely important. To test that, we built 2 simple prototypes with different variants for each. The first one combined control point mechanic and PCG. When a team captures a point, we spawn visuals around it, as well as new extra control points. Expanding the gameplay area up to a defined grid size. The team controlling more than 50% of the area wins. The second prototype is an infinite runner, where a single difficulty variable is incremented every time a player crosses a tile. This variable is then impacting the results of the upcoming tile, by increasing the density of what's coming up. And we made also a quick alternate version by adding a random rotation to those tiles, and then we updated the PCG graph to have arrows indicating where the player should go, and that was done fairly quickly. Actually, these multiple prototypes were built under 2 weeks by only 2 technical artists. And it allowed us to confirm that having that framework working at runtime within Unreal Engine for in-game and multiplayer content is an idea totally worth pursuing. Ultimately, we think that this framework can bring new gameplay opportunities for game devs. Next, we wanted to attack scale and speed in a much higher density in a large world. The demo was about switching realities using Fortnite, City Sample, and Quixel content. Here in the video, you can see the Fortnite variants being generated live during gameplay. It is made of 4 different PCG rules. It is made of a single PCG rule with 4 different presets. And they're applied when the player goes through those portals. To achieve this, we had to build a custom hierarchical generation logic in Blueprint as a way to support level of detail based on distance and orientation from the player. This hierarchical generation concept is to be implemented natively in the framework in the very near future. As with the gameplay prototype, this was all running at game time in a quick build, without any pre-generation during the quick time. Working on these really helped us on improving performance, multi-threading, scale, and parameterization. But, well, that's not all. We had to build well-building tools prototypes. We want this framework to be used by artists and designers to create their own tools for their own project needs. It's an open framework. It is not limited to a single task or domain. In this video, you can see the interrupt with the geometry tools to separate biomes using volumes, which are then processed within the PCG graph. But we obviously had to try some building generators, or it would not have been called PCG, right? So the first one here shows handles to define the footprint of the building, and then construct it using City Sample City Sample nanite modules. The second prototype here is a little bit more involved, as it's reproducing the concept of a defined grammar as used in the Matrix Awakens buildings. For each floor, the grammar is set within the node graph in this case, and adapts to the spline driving the footprint. So after seeing the great assemblies that the Quixel team was producing for this demo, we thought that it was a good opportunity to start looking about how we could be leveraging and crafting and procedural all together. We started working on what we call the PCG assets that can be used inside as instance nodes within the node graph. These assets basically stores a point cloud of all visuals contained within a level, with a full set of attributes, such as the mesh and material references, the scene hierarchy, and actor tags. With all that information accessible, it is then possible to augment these assemblies through procedural logic and increase iteration speed and quality overall. The lower half of the video here shows you how simple the rule actually is given the results above. You can also see the attribute list view being updated live as I'm extending the spline and enabling disabling nodes. The asset utility is distributed with the PCG plugin, so you can use it, just improve it, or use it as an example to create your own PCG assets type if you want. All of what I've shown here so far proves that we need to build for extensibility and interactivity. Effectively, what we want to do here is to blur the lines between procedural and traditional workflows. We believe that procedural tools should always help artists and designers to reach the best quality possible in the project's given time. Okay, enough of the prototype work, and let's jump into Electric Dreams. That was a nice music. Okay, so our objective with this demo was to show how scalable the solution already is, using everything that we've learned and developed so far. We are literally generating pebbles up to the large Vista mountains in the background. We have 8 unique PCG graph total in this world, supporting complex multi-graph interactions and full parameterization. And we're also leveraging the concept of the augmented PCG assemblies that I've just talked about. Now, what we call the close-range PCG area is made of 4 of the 8 PCG graphs. There's the small and large assemblies, the ground, and the embankment sides surrounding the area. Within the PCG graph, you can get data from actors, and you can get even outputs from other graphs. The ground rule is a perfect example of multi-graph interactions because it's using all of its neighbors to construct itself. It starts by getting the embankment spline to create its surface. And then when adding the assembly to the world, the graph gets updated. And during that update, we compute a distance field to rotate points around the assembly to better conform them around its shape. Using our debug visuals that can be customized and applied to any node or to multiple nodes at the same time, we can see here the ground surface following the embankment spline and what's actually happening underneath the assembly when it's present in the scene. By moving that assembly left and right, we get callbacks triggering the graph update, and we respawn everything that has been changed by that manual interaction. The ground rule is not the only example with complex interactions. The large assembly itself is also aware of the embankment and the small assembly next to it. A good example is the fallen tree logic within that rule. The surrounding spline is used to find potential fallen tree target position, which are represented by the blue wireframe box in the image that are quite hard to see, I'm sorry. By testing for overlap between the potential fallen tree bounding volumes and these targets, we can define if the tree should be spawned horizontally, pointing down toward the ground, or just discarded completely. We can control the probability by adjusting the number of potential targets in trees, but we could also use helpers to precisely place one specific fallen tree if we wanted. Speaking of helpers, in the large assembly, we added lens-slice manipulators. And these can be used to customize the assembly interactively with full manual control. And then it was super easy to integrate the same logic when we are approaching the small assembly next to the large one. And this is the kind of interaction that we expect you to build and expand on when creating your tools with this framework. Now, the PCG asset prototype shown a few minutes ago has proven to be extremely useful. And that's quite a blinding image. In the upper right corner of the image, you can see the procedural assembly with all of its modules. And the same applies to the embedment rule, where we have specific modules with specific functions, such as the 360 lens slide on the left that can be virtually placed anywhere because, well, it can be rotated, right? And everything in there is scattered along the spline using the segment length, the curvature, and even overrides to address specific art direction calls. But we can also use world raycast on a surface as a surface to sample on. In the case of the clover patches here, we're actually raycasting on the output of the graph itself. Placing such assets using raycasts can return invalid position and causing orientation and floating issues. So we fix that by creating what we call the flat area detector, using the subgraph feature, just like a material function that can be reused. Within that function, we reproject at the corners of all of these patches and define if the object can be safely placed or not based on overlap and orientation of these extra points. So notice the red debug points on the left, and where it's a little bit more flat on the right, we get a lot of green, and that's where you'll see clover being spawned. And this is shown at a very, very small scale, but you can imagine that we're using exactly the same subgraph and the same logic within the forest to spawn rocks at much larger scale. In most cases, we use a static mesh spawner node that outputs optimized instance static meshes component on the actor holding the PCG component. It's not only the most optimal output for the engine, but it's also fully customizable as we've exposed ISM descriptors that can be edited per entry. And these descriptors, you can also create material overrides. And you can even use material overrides by going through per point attributes. And that's what we did a lot in the demo. But we're not limited to ISMs. We can spawn actors, and we have to, obviously. In the case of in this case, we're spawning dynamic rocks and plants all over the area, and we're even excluding the car bonding volume. And excluding the car bonding volume is not a new idea. Remember, in the gameplay prototypes, what we had to do is remove the player from the spawning of the assets, because we don't want any assets being spawned on top of them during gameplay. Okay, let's jump onto the long range. The remaining 4 rules are the vistas, the mountain and base forest rules, and the fog cards. And pictured to the right, which is there, we have the forest graph, which supports the most interaction and customization within the demo. As you can see in this video, we've exposed a set of parameters to quickly exit the forest life. Those parameters come from variables on the blueprint with the PCG component, and then are read back within the graph. While this will always be supported, as Julien said earlier, we're currently actively developing our graph instance system, where you'll be able to expose the parameters directly from within the graph. So you don't have to go through blueprints and variables to do so. A little bit like material parameters, where you want to edit them into the material instances. Okay. The forest rule is following what you would expect from a procedural forest, where primary assets such as rocks and trees are surrounded by their own secondary and tertiary assets. And the rocks and the cliff are also removing all of the trees that are overlapping, so we don't have bad overlaps in the forest. And in the same way, we exclude the entire handcrafted area, as well as the PCG close range area that I was talking about earlier. And we are even mixing both the mountains and the base forest rules together to blend them using, again, a subgraph with logic based on height and normals. You can see in the video that's live with the debug display applied on multiple nodes. Using the same parameterization approach, we built different presets for each layer of the Vista rule. The idea here is that we can have different configuration, store them, and apply them when needed, such as an in-game event, or a cinematic, or just multiple shots of a movie you're making. But you could also use those graphs into multiple worlds and across production and project. And within all of the rule of the demo, we heavily rely on attribute operations. And through those operations, we scale things based on distance. We create stacks of mountains and call trees behind those mountains. We reorient the fog cards toward the center of the world. And we even apply different vegetation material overrides per single tree in the forest based on the sun direction. And you can do so much more. To end this part of the presentation, these are some stats for each rule. The timing represents the total time of all nodes added together. Keep in mind that for us, runtime and live editing is one of our main focus, and we'll always keep improving on performance. But we think that it's already quite impressive considering the fact that we're experimental and that we're spawning over 1.5 million assets total in this world. And that's a 4x4 kilometer world. Now, if you're at GDC this week, please see us at the booth today or tomorrow, or attend the PCG tutorial at the Learning Theater. And if you could not make it, look out for the tutorials videos that we're going to upload on the UE Dev community website. But before heading off to the incredible physics simulation work done in the demo, and trust me, they're incredible, I want to say a huge thank you to the entire PCG Framework development team, as well as the Electric Dreams crew. Up to you now, Bryce, and thanks for listening.
So hi, my name is Bryce Criswell. I'm a lead physics engineer here at Epic Games, and I'm going to talk about some of the physics features we used for this demo. So first of all, we are very excited to have the opportunity to partner with Rivian this year and explore setting up their R1T inside of the Unreal Engine. We decided to use this as an opportunity to highlight some of the features in our vehicle system, our fluid system, and a new tetrahedral solver that models volumetric soft body dynamics. So first up is our vehicle system. The Chaos Vehicle plugin was utilized during the city sample demo for the destructible vehicle system and has been available within the engine since release 5.0. This version of our vehicle system allows for skeletal mesh-based vehicle setups, where we perform scene queries from wheel positions to emulate the suspension characteristics of a vehicle. And we also provide a torque model to help recreate a typical transmission-based drivetrain. So for this demo, one of our first additions was that we needed to add the ability to emulate the Rivian drivetrain, where each wheel has its own electric motor. So specifications regarding the torque and energy distribution of the Rivian's R1T electric motors was directly discussed with Rivian engineers. Our current system provides a maximum torque that is divided between all the active wheels of the simulation. However, for a Rivian, each wheel is computer controlled, and the energy is directed to the necessary wheel based on its interaction with the environment. For example, the wheel with the highest coefficient of friction will be given the most power, and it can provide the best traction for the vehicle. This means that the wheel motion for the Rivian's drivetrain is much more precise than a standard vehicle model. So for this demo, our goal was to model the rock crawl mode of the Rivian. This means that the throttle input was reduced to limit the full power of the electric motors. The torque curve was cut after 20 miles an hour, and acceleration was limited to emulate the feeling of a four-wheel drive's low gear setting. Now, keep in mind, the Rivian doesn't actually have a low gear, but it feels like that when you drive it in this rock crawl mode. It moves very slowly with a precise motion over a tough terrain. We used the existing engine braking parameters to simulate the effect of the motor's regenerative braking system. We set the transmission to have one forward gear and experimented with finding an underlying gear ratio within our vehicle that matched that of Rivian's. Resistance values were tuned in the interface to make the vehicle quickly deaccelerate when the throttle is not applied, which aids in the controllability when driving it downhill. But again, it was just more to emulate this four-wheel drive setting for the crawl mode. So the adjustment of the throttle and the braking parameters were all managed through our existing controls in the vehicle system. However, the Rivian's R1T had a few features that were not completely represented in the plugin, and we needed to add them. The most obvious differences were the wheel spin characteristics and the complex behavior of the R1T's dynamic suspension. So first, Rivian prides themselves on their ability to not over-rotate a wheel or slip or spin out a tire. Our simulation already had traction control, but we added a maximum spin threshold, which prevents the wheel from rotating too quickly when it's off the ground. Rivian indicated that the wheel will just slowly turn until it finds the ground again, and we incorporated that behavior into our model. The different drive modes advertised by Rivian will allow the drivers to control the height of the vehicle from the in-vehicle display. The rock crawl mode will raise the vehicle to 15 inches above the ground, while the sport mode will reduce its height to 9 inches. To emulate Rivian's ability to transition between the different drive modes, a new function was exposed to blueprints that allows artists to modify the suspension height of the vehicle at runtime. Considering the pace of the demo, only rock crawl and all-purpose mode were modeled for our asset, and sadly, the 0 to 60 in 3 seconds for the sport mode was not. So no driving game today, or racing game today, sorry. So let's transition now and talk about the Niagara fluid system. The water feature you saw in the demo was a real-time fluid simulation authored within Engine. The Unreal Engine's Niagara-based fluid system was released in Engine version 5.0 and offers artists and end users interactive, real-time water simulations. The toolset is fully incorporated within Niagara and controllable using standard gameplay setups. Over the past year, updates have been added that improve upon the system's capabilities and workflows. The Niagara fluid system supports a 2D and 3D gas and water simulation. With the interface completely built within Niagara, the artists are encouraged to explore the feature set, inspecting our predefined template workflows and mixing and matching features to achieve a desired look. As an artist, you are encouraged to tinker. As an engineer, you are encouraged to learn from our source and contribute through GitHub if interested. Niagara's tools provide several levels of abstraction for an artist when building setups and workflows. Here we see on the left an example of an emitter's summary view, which provides high-level simulation controls that simplifies an artist's interaction with the fluid system. However, as an expert user that needs a more fine-grained level of control, the emitter's underlying implementation is still available to expose all aspects of a complex effect. That's on the right. Artists will interact with the fluid system using engine blueprints. As you can imagine, blueprints provide artists with gameplay controls over the real-time environment, allowing for event triggers that can start and stop a simulation, control collision interactions, allow artistic direction using fields, and direct the fluids with velocities. Of course, if real-time is not your thing, and you need to utilize a more traditional visual effects pipeline for cinematic-based workflows, you can cache your simulation results and play them back within Sequencer. So for this example, we are running a live sim in Sequencer with a keyframe controller. We adjust the collider's timing to get the desired look, and then cache the fluid sim with a simple button on the cache track. We can then scrub the results or render using the cache, thus avoiding a heavy simulation every time we need to render the results. The liquid solver is based on the fluid implicit particle method, also known as FLIP. The solver simulates water particles moving through a voxel grid that defines pressures from the velocities of the particles. To represent interactions with the environments, collisions are stored as boundary conditions within the grid and prevent the flow of particles through scene geometry. Ultimately, the FLIP solver produces a velocity that gives a plausible, divergent-free motion, which can then be transferred from the simulation grid back onto the particles. Finally, to visualize the results of the simulation, the particles are stamped into a sign distance field so that a surface volume can be generated for rendering. The sign distance field is then smoothed to reduce noise artifacts introduced by the rasterization of the particles on the grid. Once the simulation is complete, surface particles and secondary effects like wet maps can be layered on top of the simulation results to add to the next level of realism. Here we see an example of a secondary particle adding a whitewater effect to the surface of the fluid. Also, within the demo, you will see trails of water that are left from the tires as the vehicle leaves the pond. To integrate this fluid setup into the Rivian demo, our artists first pre-computed the ground sign distance field that produced a watertight cup for the fluid particles. The Rivian was represented using mesh distance fields that pushed the water away from the vehicle. Also, the initial state of the pond needed to be still and glossy to kind of indicate the untouched nature of the surface. To keep the fluid in a perfectly still state, a trigger volume was created to freeze the velocity from within the blueprint. Similar trigger volumes were also utilized to hide the simulation when not visible, saving valuable resources on the GPU. Another aspect of bringing a bit more realism into this demo involved modeling the interactions of the tires with the environment. We utilized a tetrahedral simulation to model the deformations of the tires as it interacts with the terrain. This is a real-time simulation that constantly adjusts the relative volumes of the tetrahedron as it interacts with the environment and is gameplay directable through the use of animation constraints. The Chaos Tetrahedral Solver offers a stable, real-time simulation framework for the evaluation of volume-preserving lattices. One of the benefits of this solver is that it effectively gives us a dial to control accuracy versus speed depending on your target application. This is a CPU-based simulation, which is advantageous for several reasons. Rendering resources on the GPU can consume a significant amount of hardware budget due to the resolution of the geometry in the environment or the fluids or whatever you have going on the GPU. And also, having access to the deformable simulation on the CPU allows us to start exploring deformable models as gameplay affecting elements. For the Rivian simulation, we were targeting speed. The results needed to run on a reasonably high-end PC and remain stable and artifact-free, which can be quite a challenge for dynamics across volumetric meshes. For example, the density of the mesh, or just the number of connections across the mesh, can dictate the iteration requirements of the solver. As a result, a denser mesh will require higher iteration counts to properly propagate the energy through the system. Therefore, a balance needs to be found that allows the mesh to remain visibly plausible, but performant and within budget. So I intentionally added this bottom video to make a point about convergence and mesh resolution. The noise artifacts we see on the lower example are an indicator that the simulator is not taking enough iterations and will need more time to resolve. Unfortunately, this means that you will not be able to run at this level of detail in real time, and will need to consider reducing your resolution. If you actually need this level of detail in your simulation, you will need to consider our in-engine cached solution to get reasonable results, and then potentially play back a cached canned animation inside the simulator, or inside your game. Okay, so the tire's simulation geometry is modeled using a radial tetrahedral mesh. We experimented with different radial meshing techniques to help explore the bending characteristics of the tire. In this example, we are testing an isosurface stuffing tetrahedralization from Tetwild, which will be released in 5.2, along with a radial tetrahedralization algorithm developed for the demo. By varying the structure and density of the mesh, by varying the structure and density of the mesh, we can see that the simulation will produce dramatically different results. And we use those results to help configure the iteration requirements of the solver. The tetrahedral asset that drives the tire's geometry is also configured using an evaluated node graph, which assists in the procedural authoring of simulation setups. So the vertices of the tetrahedron along the wheel's rim are constrained using kinematic constraints, also known as infinite mass attachments. The constrained vertices will follow the rotational animation of the axle produced by the vehicle system as the player drives around. The connected tetrahedron that are not constrained by the animation are then carried along for the ride. And while the tire was affixed to the wheel using kinematics, the interaction with the environment was accomplished using raycasts through vertices along the surface of the wheel. The raycasts provide contact information at user-specified control points that then push the surface of the tire out of the ground geometry. This setup allows artists to configure the accuracy of the tire's interaction with its environment and also tune the resolution of the collision response based on CPU limitations. Collision interactions against dynamic geometry were also added using convex and analytic collision objects along the path of the demo. The vehicle will stream dynamic geometry into and out of the solver based on the proximity to the wheels. Here we can see the tires interacting with the dynamic rigid bodies as the vehicle drives through the environment. Lastly, to see the results of the simulation, we transfer the simulation mesh onto a higher resolution surface for render. This approach can target both nanite and skeletal mesh geometry types. For the Rivian, we are using texture maps to deform the nanite geometry. However, skeletal mesh deformations can be accomplished through an Optimus deformer as well. And I want to just pause here for a second and express how impressed I am with what the rendering team has been able to accomplish. This tire is roughly 1 million vertices, which is a very high resolution for a deformable gameplay asset. Being able to push the deformations into such a high resolution surface has really helped sell the realism of the tire. So the Rivian is just one example of how you could perform a deformable simulation in Engine. Because the solver we are using allows for convergence if you allow it to take enough time, you can also use our solver to produce cached, high-resolution simulations that can be played back within Sequencer. For example, this shows a multi-layered muscular skeletal simulation where the underlying muscles are simulated against the skeleton. On the left, we have a passive muscle simulation of a character against its animation. On the right, we see a fascia layer simulated on top of the muscles. Sorry, that first frame did not play. So please note, this example is not a real-time simulation and is experimental in 5.2. But it could be used in a character training pipeline to construct an ML-based GPU deformer if you want a real-time solution on the skin. So if you would like more information about our ML-based character simulation pipeline, please see our 2 o'clock talk, Metahumans, Framework, and Machine Learning for Next-Gen Character Deformations. So lastly, here's another look at the different elements coming together. The vehicle constraints, the fluid system, the deformable tires, all simulating in real time. Everything that we have shown here is available in the 5.2 release. Details for the Chaos tetrahedral simulation will be posted on the Community Learning channel in the coming days, alongside the existing documentation for the Chaos vehicle plugin and the Niagara fluid system. And I also want to give a big thanks to the Chaos simulation team. It has been a tremendous amount of work to get us to a point where we can show these type of simulations, and we are all very excited to show the world what we can do. So please come by the booth if you have any questions. And now I'd like to introduce Marion, who will be talking about our new material authoring system. Thank you.
Thank you, sir. All right. Hello, everyone. My name is Marian Alaoui. I'm technical artist for Epic Games, part of the Special Effects team. Today, I'm really honored to present you Substrate, the new layering system for Unreal Engine 5. The beautiful jungle demo called Electric Dreams demonstrates this new powerful feature that improves a lot the visual fidelity. All materials in this demo are using this new material system by simply enabling the option in the project settings. But now, let's talk about what is Substrate and how is it working. Before going into details, it is important to understand one of the core features. In traditional real-time rendering, reflection is calculated by merging all the parameters all together to output a final specular that's going to be more or less accurate. With this new system, Unreal is able to separate each reflection for each layer by calculating them separately, and that's going to output the result for you. With this in mind, artists will be able to work with accurate material based on an optimized multi-specular, also called multi-BSDF, that will increase the visual possibilities. By upgrading the new material graph, Unreal is offering more flexibility with less complexity by merging multiple shading models into a single node. Default lit, subsurface, skin, and fuzz would be all merged together. Each layer in Substrate are composed by an interface, here in yellow, and a medium in blue. Substrate help to reason about what we manipulate and how light would interact when dealing with those properties. Every node we are playing with are allowing physically accurate transition, but still allowing artists to do some variation and explore different art styles. Each substrate element will generate a spatial topology, allowing the engine to easily reorder the layering system. Substrate is coming with a new node called Slab that offers a lot of advantages. With parameters, you can create a huge variety of materials that could combine different shading models into a single asset. Each BSDF is represented as matter, where stacking them together is resulting in a variable list of packed bytes that will change based on the complexity of the material. You can compare this, like this topology of the system, to a G-buffer, for example. This adaptive storage enables per-pixel topology and features scalability that provides a range of optimization without sacrificing the quality. This is one of the key elements of Substrates. Don't lerp anymore, just use Substrate operators. The new layering system allows you to physically transition between matters such as dielectric and conductors. Parametric blending is allowing per-layer optimization that gives you freedom to choose between performance and quality. Note that this is going to be inside the different operators I'm going to show you just after. Substrate is offering you two main types of composition. Horizontal, that will mix the two slabs on the same depth, computing both specular individually to mesh them together. And the vertical composition, that take into account the thickness or the depth of the top layer to apply transmittance and proper absorption based on your inputs. Finally, the weight coverage node that is working similarly to an opacity layer, where you will be able to change the opacity of a specific slab that is also working per pixel. This is very useful, as you could remove the entire slab from the material evaluation when the coverage is set to 0. If your project is currently using the old material system and you would like to upgrade to Substrates, you will be able to use the Substrate legacy conversion that allows you to automatically make your old material compatible with Substrate. When enabling the option, all materials will be automatically converted using that node. You don't need to do any kind of manual work for this. But now that we covered the theory, let's go for a few examples that's going to be better. One of the best updates is giving the opportunity to transition between dielectric to metallic, for example. In this video, you can see the nice transition between the two types of matter. By calculating two separate BSDF, Substrate will render the transition with accuracy. On the right, you can see the material graph composed by a horizontal layer blended with a mask texture. This example is a bit different, as you can see. Substrate is now allowing artists to play with the F0 and F90 values. This new functionality increased the possibilities by keeping the result physically correct. The F0 and F90 has been added to the slab to facilitate the control. Here, you can see the simplicity of the material graph by simply giving the two colors directly to the nodes. We also extend the possibility by adding a thin layer node. This is representing a layer of matter, that absorbs part of the light and allowing you to see this very nice chromatic effect. You will be able to play with the various parameters, such as IOR, normal, and thickness, to vary the results. It is important to keep in mind that this approximation is based on the view angle only. By upgrading our new shading model, we are now supporting the second roughness as a default feature in Substrate. This will give you more control over the shape of the tail for the specular by just creating a new node called haziness. This is going to simplify the work a lot for you. The first model has been also improved a lot. The artists will be able to have more flexibility and will be able to work way better with this new shading model updates. Simulating the fuzz with improved physical representation will make your material more natural than ever. The rough refraction is a new feature implemented in Substrate to facilitate the process of creating rough layer by blurring the bottom layer for the opaque material, for example. But here, as you can see, this option is also working with translucent material by blurring the scene color based on the depth. With this option, you don't need to do any custom tricks anymore. This is just working. All right, now that we covered some simple example, I would like you to go for a more complex one. We're gonna rebuild together the nice uphole effect we used in the Electric Dreams demo you saw just before. In the first place, we will create the bottom layer representing the back of the element. To increase the depth filling, we will create a fake refraction effect that's going to be based on normal and the view angle by changing the specular. For this, we will play with the F0 and the F90 we just saw before. In order to decrease the strong contrast of the specular highlights, we will use the new haziness node to grow the tail in order to affect the reflection. The middle layer is a bit more complex. The idea is to add this nice chromatic effect created by the topology of the piece. We will first generate the parallax occlusion to simulate the 3D model inside the material. Then, by reading the depth saved in the texture, we can sample the material information directly inside the vertical layer. It is important to imagine this layer as a translucent matter that absorbs a certain range of the light in order to reveal the bottom layer. An additional anisotropy effect is used to break this linear reflection, giving a more natural look by playing with the tangent, for example. By adding a coating layer, we will increase the depth of the parallax effects. The clear coat, similarly to the previous example, will also use this substrate transmittance mean-free path that simplify the mathematical representation of the transmittance, giving us the opportunity to output the final color based on the thickness or the depth. You could imagine this coating has a thick piece of tinted resin, for example, that have been polished. Finally, let's add some dust onto this multi-layer material. By simply adding another vertical composition node, we can properly generate and calculate all those complex BSDF that are all very different. One of the advantages of substrates is the possibility to split each group of matter as an individual pieces on your graph, which gives the artist a clean material asset, which is very important. You can also use material function to clean your work in order to help the readability of the material. All right, with all those effects, you will need to control the performance impact of your creativity. To help artists and engineers to have some feedback, Substrate is coming with different tools to dig inside this layering system. Various view modes have been added to track your material complexity. As you know, stacking multiple BSDF could be expensive if you're not too careful. However, Substrate will help you to find the best combination between performance and quality. The first view mode is showing the number of BSDF you have per pixel. By simply looking at the colors, you will be able to approve the usage of extra layers in your material based on your target quality. It is a very simple view mode, but it's very useful and could save you a ton of time. The second image is showing an in-depth layers or an in-depth information on your different layers. You will be able to inspect each element, such as roughness, diffuse color, and minimal values. By hovering the material with your cursor, a 3D gizmo will help you to analyze each normal of your material. An additional information will be added to the screen in order to visualize the performance impact on your memory. That is very important to keep in mind. The last image is an example of many advanced view modes you have in Substrate. However, this requires to be enabled in the project setting. This UI is helping to inspect each layer and understanding how Substrate is reading your material. This advanced debugger is heavy on the performance and needs to be disabled if you are targeting for performance. It is important to note that the current system do have some limitation. This experimental feature is currently allowing the artist to have a maximum of 8 slabs, as well as a limited number of tangent space in your material. All right, so what is next? Substrate is currently not supported by the path tracer, but the team is working really hard to have it working properly. We would like you to still use both options in order to validate your result with the path tracer. As you know, a continuous effort is made by the developer to always improve the performance without losing the quality of your material. Both performance and optimization are in the radar of the engineering team. We are also trying to be listening for feedbacks in order to improve the stability of Substrate. All right, if you have any question, feel free to see us directly at the booth or attend to the session that's going to be also happening at the booth today. I would like to do a special thank you to the rendering team, especially to Sébastien Hillière and Charles de Rossier, who has been amazing creating this amazing framework. With all this in mind, I would like to thank you and enjoy the rest of the day.